This is the solar system. What's shown here is a, well, I'm just going to shut the lights off. This is meant to give you a sense of scale for how big the planets are compared to the sun, in some sense. So obviously this is the sun, and this little thing right here is the Earth. So roughly you could take the Earth and place 100 Earths across the face of the sun. And as I'll mention later, since all of these planets in the solar system, to within about a factor of 5, have the same density. The density of the sun is pretty close to the density of water, for example. That means the masses of the planets scale like their volumes. So since the radius of the Earth is about 100 times smaller than the radius of the sun, if you want to calculate how the volumes scale, the volume goes like the radius cubed. So the volume of the sun is 100 cubed times bigger than the volume of the Earth, which is 1 million. It's about 1 million times more massive. Jupiter is about 10 times bigger than the Earth in terms of size, and that makes it about 1,000 times more massive. Not exactly, it's actually closer to 300 times more massive, but that's in the ballpark. What's amazing too is we know the colors of the planets, we know what they look like in great detail. That's partly because our telescopes are so good, and in many cases because we've actually flown space probes and orbited around them and really studied them in great detail. As you may know, there's some discussion these days about different types of objects that orbit outside of the sort of classical planets. Pluto used to be in this list of planets. Now it's been demoted to something called dwarf planet. And there are these other little dwarf planet things that are orbiting around outside the solar system in slightly funny orbits compared to the sort of classical planets, which are mostly orbiting in ellipses, but that are very close to circles in one plane. Okay. Now, it should be, I think people realize when you look at a picture like this, Jupiter is not this close to the sun in relative size. Okay? It's, Mercury is not sitting right up against the sun on a scale like this. In fact, it's actually quite difficult to even comprehend how far the planets are away from the sun when you try to place things in a size scale. And there are lots of different games that people play to try to, gain some intuition about this. And here's something that I found someone did that I thought was pretty good. There's an astronomy professor in Florida who said, well, let me try to do this on a Google map. So he finds Google Map, and he gets a size scale. So this is about 200 meters. And on this scale, if you put the sun right here with this thumbtack, this would be the locations of the other planets along that scale. Okay, so that's interesting. But on this scale, the sun is squished down to a size of about 1 meter in diameter, so a blown-up garbage bag. So you place a blown-up garbage bag here near the coast, and then, let's see, about more than 100 meters away is the Earth on that scale. And the Earth is the size of a blueberry. Okay? And then Jupiter would be about the size of a basketball, and it would be sort of, 500 to 700 meters away, something like that. And we've talked about when you do things like this, and you try to try to expand it out even more, where would be the nearest star on this scale? Okay, remember, I think I told you that if you made the sun the size of a basketball, the nearest star would be in another state. On this scale, the nearest star would probably be something like, almost to the moon. I mean, it would be very, very far away on this scale. So this just gives you a sense of just how big the solar system is, a rough sense of the relative size of the planets. Here are just some numbers for you to, if you're interested. These are a little bit more exacting than the ones I was giving you before. So the sun is about 300,000 times as massive as the Earth. So my estimate I gave you was 1 million, but for astronomers that's good enough. You're in a factor of 3, you're happy. So the sun's about 1 million times more massive, or sorry, 300,000 times as massive as the Earth. All the other planets here are listed in units of Earth masses. So for example, if you can read it, Mercury is about 5.05 Earth masses, so about 5% mass of the Earth. Jupiter is about 300 times the mass of the Earth. And Neptune is about 17 times the mass of the Earth. These are densities here of all the planets, and as I told you, they're all the same to within about a factor of 5. So this is just a common unit of density, grams per cubic centimeter. So cubic centimeter is a volume, and grams is a measure of mass. So mass per unit volume is density. So just to sort of, water is 1 gram per cubic centimeter. So the density of water is here. The Earth is somewhat denser than water because most of the mass of the Earth is in rock. And the density of granite, for example, is 3 grams per cubic centimeter. So the inner planets, you'll notice, are very dense. And the outer planets are less dense. The inner planets are called rocky planets because they got a lot of rock and heavy stuff. And the outer planets are called gaseous planets because they're less dense and they're mostly made up of gaseous material, low density material. Okay, so this is our whirlwind tour of the universe, of the solar system. Well, what I wanted to do is in addition to kind of introducing you to some basic things about the solar system, there's other things about the Earth's orbit and what's going on that actually affect us on a day-to-day basis. And I just wanted to make sure, you take an astronomy type class in college that you know some answers to some basic questions. So one of the things I hope everybody knows, if you don't know right now, is why do we have seasons? So why is it hot in the summer and why is it cold in the winter? Yeah?
Because of the tilt of our axis, the Earth's axis.
Okay. Does anyone else have any other ideas? Yeah?
The way that in summer is closer to, at one point it was closer to the sun.
So you're saying at one point the Earth is closer to the sun than at another point, so when the Earth is closer to the sun, it's hotter. Okay. So those are 2 good ideas, 2 theories. So one of the theories is, I'll roll with this and then I'll get to your question in a second. So one of the theories is, let me just play Galileo here. Okay. So we got Ptolemy and Copernicus are giving me 2 ideas for what causes the seasons. So Ptolemy tells me, I'm not going to associate any names anymore. So someone tells me that the reason why we have seasons is that the Earth is tilted. And let me elaborate on this idea. Well, let me start with the first one, which I think is a little bit easier to digest what the theory is. The theory is, well, we were told that the Earth orbits on an ellipse around the sun, and so that means at some point during the year, it's a little bit closer to the sun than it is at another point during the year. Since it's closer to the sun, it gets more energy, and so it's hotter. And then when it's far away from the sun, it's colder. Okay, so that's one theory. The other theory is the Earth is tilted, so that it's tilted when it's tilted towards the sun, it's absorbing more energy, and when it's tilted away from the sun, it's absorbing less energy. And I'll elaborate on that idea later too. So I can do an experiment to try to tell the difference between these 2 theories. Okay? And maybe someone's already done this experiment. Has anyone ever been to the southern hemisphere? I wonder. You have? Where'd you go?
Australia.
What time of year was it?
Right now.
Was it, so it was sort of the winter time?
Yeah.
The problem is we live in Southern California. It's sort of a difficult experiment to do. But it was the winter time here, and you went to Australia. Summertime there. So, and another way to do this experiment is if I knew someone in Australia, and let's say I was someplace where it was actually cold and it was snowing, I could call my friend in Australia and say, is it cold and snowing there? And they would say, no, it's high summer. It's really hot here. It's like in the outback. I'm going to die. So in fact, what I want to emphasize here is there are a lot of people who kind of have in the back of their mind somewhere, because they've heard somewhere that the Earth is closer to the sun than it is. The Earth sometimes is closer to the sun than other times. And a natural thing to assume hearing that is that, oh, it must be hotter when we're closer to the sun and colder when we're far away from the sun. But you can test that idea with data. So you can say, well, if that was true, then it should be hot in the southern hemisphere and the northern hemisphere, at the same time, because the southern hemisphere and northern hemisphere are close to the sun and far away from the sun at the same time, more or less. Especially since I showed you how far away things are. So the relative size of the Earth is nothing. But all of the data don't jive with that. The data suggests that in the southern hemisphere, it's winter when it's summer in the northern hemisphere and vice versa. And the way we understand that is because the Earth is tilted, and that's what causes the seasons. So I think a lot of us, my guess is a lot of you have heard this tilted thing and sort of not digested it. Some of you have, some of you haven't. And then there's this sort of lingering idea that it depends on how far away we are from the sun. But I would like to end that idea right now for everybody in the room. The seasons have nothing to do with how far away we are from the sun. In fact, the orbit of the Earth is almost a perfect circle. And in the northern hemisphere, we're actually farther away from the sun during the winter. But that's a very minor effect compared to this effect of tilt. So let me explain to you what's going on with this tilt. Okay? So here's the sun, and rays of the sun are coming at the Earth. All right? Now imagine that I was sitting on the surface of the Earth, and I had like a mirror that I was trying to use to collect light. Okay? And I'm trying to collect light with my mirror, and I orient it like this. I'm going to collect all the light that's coming in. But if I took my mirror, and I'm standing like this trying to collect light, and I just tilt it like that, I'm not going to get as much of it. It's all going to come in at a glancing angle. Okay? Imagine another game. Imagine you're playing a game, and there are all these, say, plastic balls flying at you, and you had a big net, and you wanted to catch the balls coming at you in the net. Those balls you can think of as photons of light coming at you. And you wanted to catch those balls, as many balls as you could in a given amount of time. Most people would orient their net so it was perfectly perpendicular to the balls coming in, because that gives you the biggest area to catch the balls in. You probably would not turn your net like this and catch them all, as few as you could in this glancing bit. So as you tilt your net directly towards where the balls are coming, you have a much bigger area to collect the light, or collect the balls. And that means you're getting more, you can think of this as energy per unit time that you're getting. Turn it wouldn't be as good. So what happens when you're down here on this part of the Earth that's tilted away from the sun, everyone's nets are tilted. So you're not collecting as much energy per unit time. Okay? It's a similar effect if you've ever been outside in the midday sun versus when the sun's going down. You're getting more energy per area right when it's on top of you as opposed to glancing at you. It's the same kind of idea. So that's what's going on with the seasons. And so what's happened is the Earth is sort of tilted at an angle as it's going around the Earth, like going around the sun like that. So 6 months later, you have the northern hemisphere. The northern hemisphere is tilted towards the sun. 6 months later, it's away from the sun. And so this little graphic is supposed to represent the glancing bit, the only small fraction of the amount of light that's being captured by the sun there. So that's basically how it works. So I summarize this idea in text here. In the winter, the area is tilted away from the sun, causing less total light to strike it. The other way around in the summer, it's tilted towards the sun, you get more of the light. Note that if you're at the Arctic Circle, that's the spot on the surface of the Earth that's tilted to be edge on to the sun. So, in fact, the only energy reaching the ground at the Arctic Circle is sunlight that's bounced off of something to hit it. It's not directly hitting there. And that's why it's so cold on the Arctic Circle, because there's basically no sun shining directly on it ever, even though the Earth is spinning. Okay, so hopefully that wasn't too much of a digression for you folks, but I just wanted to make sure anybody who's taken this class knows what causes the seasons. Since it's so important to me that you know what causes the seasons, it's very likely going to be show up on an exam. It's tilted relative to the moon and the Earth. So you can see just barely there's a dot right there for the moon. People in the front row can see it. And there's the Earth. This is an actual image that was taken by the spacecraft, the Odyssey, the Mars Odyssey spacecraft that was sent to Mars, but on its way out, it turned around and took a picture. Okay? The distance between the Earth and the moon is about 380,000 kilometers. It's huge, very, very far. Now, this is a pretty cool thing that we know how far away the moon is. But what's even cooler is there were people on Earth, some humans, who knew approximately how big the moon was and how far away the moon was more than 2,000 years ago. And you might ask yourself, well, how is that possible? I mean, you might ask yourself, how is it that we know how far away it is now? Right. So, I thought I would go through this example of how initially this was figured out as an example of us beginning to sort of build this sort of very coherent and precise picture of what the solar system is like. So the person I'm talking about is Aristarchus of Samos, who I think I mentioned before in my lecture on Copernicus, etc. So Samos is just an island here off of Turkey, and Aristarchus was living there, 200 to 300 BC. So Aristarchus was one of these ancient Greek philosopher and mathematicians who was just really good at geometry. Okay, and as I think I mentioned before, if there was a problem that you could figure out using standard geometry, there was probably some ancient Greek who did it first. So the way he thought about what was going on with the size of the moon is he did an experiment using a lunar eclipse. Okay, so we recently had a lunar eclipse during the solstice, actually in December. And although I think it was cloudy, so we couldn't see it from here. So what this lunar eclipse is, it's when the sun is shining on the Earth and casting a shadow. Okay, the Earth is sitting like this, where my fist is, and therefore the sun casts a shadow. And so, my fist is the Earth, and the moon just happens to, we see it here. We see my finger lit up by the light of the sun, which is the projector. But when my finger passes behind my fist, it's no longer lit up. So that's what's going on with the lunar eclipse. And people understood this for a very long time. Okay? Remember, with all of these sort of ancient, the Greek picture of what was going on with the solar system, no one doubted the idea that the moon was going around the Earth. Okay, that's okay. As long as stuff is going around the Earth, that's cool. And that was the idea. The moon is going around the Earth. So it was understood that this is what's happening with a lunar eclipse. I mean, at least many people understood this. So think about what's going on then. The moon is moving, right? And there's this shadow that's being cast, and the moon just passes through the shadow and then comes out the other side. Okay? So what Aristarchus says is, look, as long as the sun is very far away, the size of the shadow that the sun is casting is basically is the same size as the Earth itself. Okay, the size of my fist, the shadow of the size of my fist here, right, is the size of my fist. Right? It's not like much bigger than the size of my fist. Now that wouldn't be true if I put my hand really close to the projector, right? The shadow would be really big. But as long as the projector's far away, the shadow's about the size of my fist. So it's the same thing with the Earth. Aristarchus says, well, the shadow that the Earth is casting is the size of the Earth. And he knew the size of the Earth. People had calculated the size of the Earth. He had a rough idea for how big the Earth was. Okay. So what he did is he said, look, on the sky, I know how big in diameter the moon looks. I can cover it up with my thumb. So it's about the size of my thumb projected on the sky. Okay? And what I'm going to do is I'm going to time to see how long it takes to cross the shadow of the Earth compared to how long it takes for it to move its own diameter in the sky. Because the moon is moving, over the night. And let's say it takes a few minutes for it to move, from the edge of its diameter such that now it's crossed over that edge again. See what I mean? People know what I'm talking about here? So you know how big the moon is. You just ask, how long does it take for it to move its own diameter across the sky? And then you say, how long does it take for it to traverse this shadow? That is, how long is the moon dark during an eclipse and then it comes light again? As long as the moon is moving at constant speed, then if it takes, for example, 3 times as long to cross the shadow as it does to cross its own diameter, that means the Earth is 3 times as big as the moon. Are there questions about that? Okay. You will be tested on this. Thank you. Okay. So, so he's watching the moon move, right, like this. Okay. And he says, "All right, I'm going to watch and see how long it takes for the left edge of the moon to move. Let's say it's moving this way. How long does it take for the inner edge of the moon to move to a point where its outer edge was?" People know what I mean by that? Okay. And let's say he timed it, and let's say he had a stopwatch in 2000 BC. He timed it, okay, and it took 5 minutes. And then the same night of the eclipse, it starts getting dark. And so he says, "Oh, okay, I know the moon is passing behind the shadow of the Earth. I'm going to start my stopwatch and just wait till it comes out the other side." Okay? As long as it's moving at the same speed, let's say he says it takes, 15 minutes for it to come out the other side. Then that means it traversed a distance that is 3 times as long as it traversed in crossing its own diameter. Okay? So that means its own diameter is 1/3 as big as the shadow that it just crossed through. See what I mean? Okay. Please ask if that doesn't make sense. Like, ask very specific questions if that doesn't make sense. Yeah?
Okay, so essentially, he used the lunar eclipse to tell, I'm not sure what he used to compare the diameter of the moon and of the Earth and how that had in reference, how that was in reference to the sun.
Okay, so let's forget about the sun for a second.
Okay.
The sun is just something that's casting light this way.
Yeah.
Okay? And it's like, the sun is like this projector, and my fist is the Earth. Okay? So you see this dark spot. That's like the shadow of the Earth. See what I mean?
How do you see the shadow of the Earth?
We don't see that, but it's interpreted as part of the model. So here's the interpretation of what's going. Let's do this first. Here's the interpretation of what's going on with the moon during a lunar eclipse. So here's the shadow of the Earth. Let me find something bigger than my small fist. Here, that's a big fist. So let's say this giant, Shaquille O'Neal's fist here is the Earth. It's casting this shadow. Can people see it on the projector? Hopefully, kind of.
Yeah.
Okay. And this thing is the moon. See how it's lit up? You can see it. It's lit up by the light of the projector. And you see the moon, most of the time. But every now and then, the orbit of the moon passes through this dark spot. And when it does, if we're on Earth looking at it, suddenly it gets dark. Because when it's up here, we can see it. But when it's down here in the shadow, we can't. And then it stays in the shadow for a while, and then it passes out of it again. So that's the interpretation of what's going on with the lunar eclipse. Okay? And what Aristarchus said is, all right, if that's really what's going on, then I can use that to figure out how big the moon itself is relative to the shadow that's being cast. Okay? And so let's imagine how we would do that. let's say, okay, I'm going to just count and figure out how long it takes this thing to cross its own diameter. Okay, so I'll say, all right, well, it starts here, and its diameter is this big, and I'm just going to wait till it moves that far.
So he pretty much just used the moon during the lunar eclipse to measure how long it took to cross here when it was in the moon.
Exactly. That's what he did. So he measured, he said, all right, well, it starts here. I want to see how long it takes to go its own diameter. Let's say it was 5 minutes. And then it passed in the shadow, and it stayed there for 15 minutes, say, and then it stuck out the other side. And then he said, oh, that means this thing, this piece of paper, this thing here, is 3 times as big as this thing. Okay? And this thing is the Earth. And this thing is the moon. And he knew how big the Earth was. Okay? And if you know how big this is, and you know this thing's 1/3 the size of it, now you know how big this thing is. That's what he did. So when you do that, okay, so I'm going to use modern numbers for the size of the Earth because he wasn't quite right, but the Earth is about 12,700 kilometers in diameter. If a moon is 1/3 that size, that means it's about 4,000 kilometers in diameter. The true answer for the moon is it's about 3,500 kilometers. So it's not exactly what Aristarchus got, but it's pretty close, given the guy was living 2,200 years ago. Okay? So from that series of kind of logical arguments, he was able to deduce this. So this is a very important thing, right? The idea is, if this picture of how the moon is working is correct, then from logic, I can figure out what that implies for the size of the moon. So if this is true, then this must be true. And it's just a series of logical steps after that. Now what's interesting is, now he has the size of the moon. Okay, he says, okay, size of the moon is like 4,000 kilometers or so. But once you know how big it is in absolute terms, you can now figure out how far away it must be. Okay? In much the same way as, let's say you had no idea how far away I was at the end of the room, but you knew this thing was a foot across. You can measure how big it appeared to your eye, how much of your field of vision is it taking up, to figure out how far away it is. Okay? So I'm going to pick on you, sir. If this was like this in your face, and you knew it was only a foot across, you know it was really close to you. Okay? But if it's only covering up just a tiny fraction of your field of view, you know it's very far away. Now the moon takes up about half a degree on the sky. You can cover it up with your thumb. And if it's 4,000 miles across, 4,000 kilometers across, and it only takes up just that much of your vision, then it must be very far away. But you can figure out exactly how far away using trigonometry. Okay, so if the moon is over here, 3,500 kilometers across, and if you look at it and you measure the angle that it traverses, it's a half a degree. Okay? And what you can do is then just draw a triangle. And you say, look, I have a triangle. The opening angle of the triangle is a half a degree. And this thing is 3,500 kilometers across. And from that, I can figure out what this distance is. So you do this using trigonometry. So, for example, you have a triangle that looks like this, and this is an angle phi, and the ratio of A to B is the tangent of the angle. And although Aristarchus did not have a calculator, such that he could type in the tangent of half a degree, they did have very well compiled tables of what all the trigonometric functions were as a function of angles. They knew what the cosine of 0.1 degrees was, all the way up to 90 degrees, etc., etc. They knew what all this stuff was. And they knew this. Okay? So that means B, the distance, okay, is equal to A divided by the tangent of that angle phi. If the angle is 0.5 degrees, the tangent of very small angles is a very small number. So the tangent of small angles is small. So what you have is a pretty big number, 3,500 kilometers, divided by the tangent of half a degree. If you work that out, you'll find that that's about 400,000 kilometers. And that's pretty close to the correct distance to the moon. So in astronomy, for example, if we know how big objects are intrinsically, and we measure how big they look in angular size, we can figure out how far away they are. Or vice versa. If we know how far away they are, but we don't know how big they are intrinsically, we can back out how big they are intrinsically using these kind of ideas. Are there any questions about that? So pretty impressive for Aristarchus, right? Aristarchus, living in this island, 2,000 or 200 BC, was able to figure out that the moon is about a third the size of the Earth. From that, deduce that the moon is, 300, 400,000 kilometers away. Which is a huge, huge distance. But actually, that's not all Aristarchus did. If you recall, I mentioned in a previous lecture that there was this ancient Greek who also had a theory that the Earth was actually going around the sun. And that was Aristarchus also. And that's because Aristarchus not only knew how big the moon was, he knew how big the sun was. And he figured out how big the sun was using similar reasoning. And I'm going to roll through this very quickly, but he also used trigonometry. Okay? This is what he did. He said, all right, I'm going to wait until the moon is up in the sky and lit up such that half of it is lit up perfectly by the sun. That is, a half moon. On a full moon, a half crescent moon. Perfectly cut in half. Okay, like this. And what's going on when the moon is like that, the Earth is here, and the sun is shining light on the moon such that only 1/2 of it is being lit up. When that's the case, okay, what that means is the moon and the sun are aligned by 90 degrees when the Earth is oriented appropriately. So what Aristarchus did is he waited to a point where the moon was lit up, half moon was lit up by 90 degrees. Okay? And it just so happened it was the right season such that the sun was just on the horizon at that time. You could see where the sun was, and you could still see the moon. There's sometimes the sun's going down, and you can see the moon. It was one of those times. What he did is then he measured the angle between the line to the moon and the line to the sun. He measured this angle. Now, he knew the distance to the moon, so he knew this distance. And he knew this, if he measured this angle, then using trigonometry, you could figure out this distance too. Okay, and what he measured is, he actually measured an angle like 87 degrees, but the real angle is like 89.8 degrees. It's really, really small. It's almost 90 degrees. It's very, very hard to measure those kind of angles, so we're not going to give Aristarchus too much trouble for that. But he came close to getting the right angle. And what you use to do this, you can say, well, if this angle is phi, if you recall, the cosine of that angle would be the distance to the moon divided by the distance to the sun. But he knew the distance to the moon. He measured this angle, so he could figure out the distance to the sun. And if you do this, okay, cosine of that angle you measure is the distance to the moon divided by the distance to the sun. We know the distance to the moon. We know this, so we solve for the distance to the sun. Distance to the sun is the distance to the moon divided by the cosine of that angle. Now, the cosine of angles near 90 degrees is very, very small. So you have a very big number already divided by a very small number, and so you get an even bigger number, and that number is 150 million kilometers. And that, again, is Very, very close. I mean, I've sort of tweaked my angles so I knew the answer coming in. But if you do that, you basically get the right answer for the distance to the sun. Now, Aristarchus got a distance that was slightly smaller than this, but it was still very big. You know, it was still about 100,000 kilometers or something. Okay. The bottom line is, he knew, therefore, so this is what he had deduced, right? He had deduced that the moon was far away, but the sun was even farther away. The sun is like more than 10 times farther away than the moon. Okay? But there's another thing that you notice. I don't know if anyone's noticed this. Like if you think about how big the moon is on the sky compared to the sun, they're about the same. Okay? I can also cover up the sun with my thumb. So on the sky, the sun is, that big at arm's length, and the moon is that big at arm's length. They're about the same angular size in the sky. So if they appear the same angular size in the sky, but one thing is more than 10 times farther away than the other, that means that other thing is very big. Okay. That is, if you line up another way of saying is, if you line up your pencil eraser with my head, there's some way you can do it such that they're the same size, right? My head is much bigger than the pencil eraser, that's because I'm farther away. So that must be what's going on with the Earth and the moon. Sorry, the moon and the sun. The sun must be much, much bigger than the moon. And Aristarchus figured that out, and he knew basically how big the sun was, and he knew that the sun was way bigger than the Earth. Much, much bigger than the Earth, like 100 times bigger than the Earth, or something like that. So what Aristarchus said is, and this isn't proof of anything, but he said, to him, it would make more sense that the little thing is going around the big thing and not the other way around. And so he proposed, as far as we know, the first heliocentric theory of the solar system, based on that argument. Now, that doesn't make it correct. At the time, you had no way of knowing that that was correct, and in fact, most of the Greek philosophers did not buy that argument and did not think that the Earth was going around the sun, for some of the reasons that I've already talked about. But eventually, Copernicus did draft a similar idea, and in fact, he referenced Aristarchus in his first edition of this idea, that the sun is at the center and all the planets are going around. And then after all of these data that Kepler analyzed and eventually the observations of Galileo, it was realized that this model works a lot better than the Ptolemaic model. Now just to clarify, the solar system of Kepler and Galileo was different a little bit, even though they had things arranged in the right way and roughly the right distances. They didn't know about Uranus and Neptune. That's because you can't really see Uranus and Neptune with your eye. So they didn't really know about them. They were discovered later. But they knew about these planets, and these planets were arranged correctly. Now, something I want to emphasize, again, is the reason why this theory of the solar system became accepted about this time, specifically in the time of Galileo, was not because it was a superior theory in some philosophical sense, because it was more beautiful or not. I mean, that was why Copernicus liked it. That's not why it was eventually accepted. Okay. Because the idea had actually been around for a long time. As I just mentioned, Aristarchus liked this idea. It was because for the first time, people were able to do observations that could discriminate between one theory and the other. Much like these observations that we did on it being wintertime in Australia when it's summertime here, Galileo could do this kind of thing as well. And the reason why Galileo could do it, and nobody could have done it before, is that Galileo had a telescope. The telescope had just been invented. He was the first person to point a telescope at the heavens and do observations. And it was with those observations that led to the realization that this is what the universe is like. It was direct empirical observation, not some philosophical argument. Now, as you recall, one of the things he was able to do with his telescope is he was able to actually image Venus in detail. And he was able to show that Venus went through phases much like the phases of the moon. What did that mean? That meant sometimes the sun was lighting up the full face of Venus as viewed from the Earth, and sometimes it was only lighting up just a piece of it. This was impossible in the Ptolemaic model. Okay? In the Ptolemaic model, Venus should pretty much always be crescent. It should never be fully lit up. But in the Copernican model, it should go through full phases as it goes around the sun relative to where the Earth is, watching it go around. And this is what you see from Earth. You see that it goes through these phases. And again, without the telescope, you could have never done this. Because by naked eye, Venus always just looks like a bright blob. Now, the other thing that Galileo was able to do with his telescope that couldn't have been done before is he observed that Jupiter had these little things going around it. And as you tracked Jupiter in the sky and you looked at it with your telescope, there were these little bright things that always kind of were near it. And if you tracked it night after night after night, you actually saw that these things were orbiting around, or at least moving always around Jupiter. And he realized that these were likely bodies that were actually orbiting around Jupiter. That is, they're moons. Jupiter has its own moons. And once you realize that, you realize, okay, well, the Earth isn't the only thing that stuff is going around. And that's another sort of knock against the whole Copernican, or the whole picture that Aristotle pushed, that everything's going around the Earth. This is a modern view of what are called now the 4 Galilean moons, and the relative sizes of the Galilean moons to Jupiter. They're really interesting objects. The moons of Jupiter are really cool things. I mean, they look neat. There's a lot of interesting stuff going on in their atmospheres. This isn't a course on that stuff, but they're just fascinating objects. Jupiter is now known to have at least 62 moons. The biggest moon is Ganymede, which is shown here on a picture relative to the Earth and our moon. And you see it's pretty big. The biggest moon of Jupiter is larger than our moon, but it's not as large as the Earth. It's in fact about 5,000 kilometers across. Now, just a comment on this. Well, let me just go on. So the smallest moon of Jupiter is 10 to the 11 times smaller than that. And it's only about 1 kilometer across. So there's a lot of stuff going around Jupiter. Jupiter is the most massive body in the outer solar system, and lots of stuff is going around it. Another thing, though, that you can notice directly from this picture is, look how big the Earth's moon is compared to the Earth. I mean, it's almost as big as the Earth. Whereas Jupiter, remember, Jupiter is 10 times bigger than the Earth in terms of its radius. But its moon is not that much bigger. Its biggest moon is not that much bigger than our moon. So one of the interesting things about the Earth, it's got the biggest moon by far relative to its size. And there are some ideas that having this kind of moon might be necessary for having a planet that eventually evolves life. Because the moon, in some sense, a lot of stuff that was going to hit the Earth hits the moon instead. It's sort of like a guardian or something. And there's interesting theories about how the moon formed relative to these other small moons in the outer solar system. Now, these other 2 planets, these outer planets, Uranus and Neptune, were discovered later, as I said, and basically they're discovered as telescopes get better, as people get better at monitoring the sky. Uranus is kind of an interesting one, though, because in principle, if you're out in a really, really dark place with very little light pollution and very few clouds or anything like that, you actually can see Uranus with your eye. And so it's a little bit surprising that people had not realized that it was a planet before. The way you realize things are planets is their trajectories in the heavens are very different than the trajectories of the stars, which effectively remain fixed if you take out the rotation of the Earth, whereas the planets do move. But the problem, for example, Galileo actually observed Uranus and thought that it was a star because it turns out when he was observing it, it was at part of its orbit where it wasn't moving much relative to the orbit of the Earth, so he just assumed it was fixed. So it wasn't until 1781 that William Herschel discovered Uranus and actually noticed it was moving substantially and realized it was a planet. There's a more interesting story with Neptune, which was eventually discovered in 1846, which is really not that long ago. The story of Neptune is actually fascinating. So, Neptune was predicted to exist before it was ever discovered. By this time, Newton's theory of gravity had been published for a long time, and so professional scientists, physicists, and astronomers were adept at using it to calculate what the orbits of the planets should be. And Uranus was always doing weird stuff. Uranus's orbit wouldn't always exactly follow the trajectory that Newton said it should. It was wiggled and moved. It wouldn't quite do what Newton's laws said it should do. And there was a couple mathematicians. The one who really did it right was Leverrier, French mathematician. There was another guy named Adams who was working on this problem at the same time. And they both were working on the idea that, well, you know what could solve the problem in the orbit of Uranus is there was another planet out there that we just can't see that's messing with its orbit dynamically because of gravity. And on September 23rd, 1846, this guy named Gall, who was at the Berlin Observatory, received a letter from Leverrier that basically said, according to my calculations, if you look tonight at this part of the sky with your powerful telescope, you should be able to see a new planet. And this is the planet that's perturbing the orbit of Uranus. And he went that night, he looked, and he discovered it. It was there. So what's interesting about this story is it's kind of like a powerful validation of Newton's theory of gravity. Because there were little funny things going on with the orbit of Uranus that we didn't know. That wasn't accounted for in the theory, given all the other known planets. But if you just stuck another planet there doing this exact stuff, it would account for it. And if you look in the exact spot it should be at this time of night, you should be able to see it. And in fact, it was there. So not only is this interesting in terms of discovering a new planet, discovering that our solar system is bigger than we thought it was, but also it's just a validation that this very simple theory of gravity that Newton worked out, in 16 whatever, was operating at the outer edges of the solar system to such precision that would allow you to actually predict the existence of this other planet. In some sense, Neptune was dark matter because it wasn't emitting any light that we could see, and it was predicted to be there, and eventually it was discovered. So what I wanted to do now is sort of branch out a little bit and talk about the ways in which we explore the universe. So remember, in the first lecture in class, I talked about, the universe is 14 billion years old. There's all this fantastical story I told you about in terms of what we think the universe is like. So how is it that we know all this stuff? And there's basically three ways that we can think about exploring the universe, because we're effectively locked on the planet. One is we can send spacecraft out into the solar system to explore things. The other is we can launch spaceships or space telescopes. We can put telescopes into space, like the Hubble Space Telescope, to look at stuff. And the other is we can just be on the ground and point telescopes up and look at stuff. And I want to put this in perspective a little bit. First, starting on spacecraft, very quickly on spacecraft, just so you've seen this kind of thing before. So Voyager 1 is this spacecraft that was launched in the late 70s. That currently is the farthest probe ever launched into space by humans. It's now about 17 billion kilometers away from Earth. So it's beyond the edge of the solar system. And it's at the point now where the sun is almost not really influencing the local temperature compared to all the other stars. So it's way out. But it's not that far out, as I'll mention before. So it's kind of just beyond the edge of the solar system. Originally, Voyager was sent out to loop around Jupiter and Saturn to study those things, and then it just kind of kept going. Now it's just sort of launching out. Of course, we send other probes to planets and moons, etc. The Mars Pathfinder, the Viking mission. This is an image of Europa. Move Europa. And this is an image actually taken from the surface of Mars. One of the exciting recent missions to Mars have been these Mars Explorers. Who's heard of the Mars Explorers, I wonder? Okay. Yeah, it's interesting that, well, anyway. It's a very cool thing, these Mars Explorers. They're basically these robots. Okay, the way they initially launched them on the Mars is, so first of all, it's expensive to launch stuff, to send stuff to Mars, right? It's expensive. To land them, you got to be careful, right? Because imagine now you've built a robot. You have a robot that's on these treads. You can't see it, darn it. It's basically like, it's got like tank treads. It's small. It's got like tank treads, and it can kind of drive around remote control wise. You've built this complicated robot that's going to study the surface of Mars. Now you're coming into the planet, and you want to get it on the planet and then have it drive around. That's not such an easy thing to do, because you're coming in at this tremendous speed. You've come all the way from Earth. You're coming in really fast. You're going through the atmosphere of Mars. Now, the natural thing to do would be like, okay, well, I have to turn my spaceship thrusters on and slow down and land. Okay. But that's very expensive. It takes a lot of fuel to turn your spaceship thrusters on and slow yourself down. That's a lot of energy. And that's fuel you have to launch off the Earth, get to Mars, and then use to slow down. So what the engineers did who decided to do this mission is they did something that sounds kind of crazy. Effectively, when this thing gets through the atmosphere, a big balloon blew up. So this thing is sitting inside of like a big cushioned air balloon that's huge. And it just hits the ground and bounces. It bounces a little bit, eventually stops, the balloon goes down, and then this thing comes out. And it worked. So I remember when I first heard about this idea from the JPL guys, I was like, but it worked. And they drove these rovers around Mars over short distances for several years. In fact, they lasted for like 6 years driving around, taking images of Mars. They found information that leads people to believe there used to be flowing water on Mars, a lot of interesting stuff like that. Originally, this idea was, this mission was planned to work for only a few months. And the reason why is these things get their power from solar power. So, the sun is hitting solar panels, and that's charging these things driving around on the surface of Mars. But there's all this dust on Mars, and so eventually the solar panels get covered up with dust, and then they don't work anymore, and there's no power, and everything shuts down. But what they found is that the energy coming on the solar panels would die off, would begin to go down, and then over about a month it would be really small, and then all of a sudden it would just go back up to normal again. Then it would go back up to normal again. And what was going on is there's actually little dust devils on the surface of Mars, like little mini tornadoes that go around the surface of Mars. And every now and then they would pass right over the solar panels of these things and clean them up. And they keep going. And they have movies taken from one rover. One rover will take a movie of what's going on over here, and there's a movie of like a little dust devil that's coming along and doing that. So it's pretty amazing. I guess they never suspected that this was going to, I thought it would. So anyway, there's fascinating stuff like that going on. The most distant probe we've ever actually landed on another object in the solar system is this probe, Huygens, named after a Dutch astronomer who discovered the moon Titan in 1655, which is a moon of Saturn. And this is very interesting. It's Saturn's largest moon. This is an image from the surface of Saturn's moon. It's an interesting thing because it looks like, anyway, the conditions on the surface of Titan are similar to perhaps the organic chemistry that was going on in very early Earths. So people want to, it's interesting to study these different planets and these different environments to learn more about perhaps the processes that were going on in early Earth, et cetera, et cetera. So there's a lot of interesting stuff in that direction going on. thing I wanted to emphasize is that Huygens is the most distant space probe ever to land from Earth, and Voyager is the most distant space probe that has ever been sent out anywhere, and it's just beyond the orbit of Pluto, or so. But put this into perspective, right? If we wanted to just send the probe to the nearest star, they'd have to go 10,000 times farther for us to send a probe to the nearest star. If you recall, the nearest star is 4 light years from us. The galaxy is 100,000 light years across. The nearest big galaxy is 2.5 million light years away. So we're a very long way from being able to actually send probes to other stars, much less throughout the galaxy, and much, much less to other galaxies. So, although these space probes are very interesting because of the detail they provide, they really tell us nothing. They really are not allowing us to explore cosmology, the big picture stuff. And the way we do that is with telescopes. And this is an interesting thing, interesting perspective to think a little bit about. Pretty much everything we know about the universe on large scales, about our galaxy, about other stars, etc., is all learned from basically just hanging out here and looking at the light that comes down. But what we do with that light is we just torture it. We get it, squeeze every ounce of energy out of it, every detail of information we can get out of that light. That's what we're doing. It's like people looking for fossils in dirt, like uncover little stuff. It's the same kind of deal with light. That light contains information. And a lot of modern astronomy is taking that light and getting information out of it and using it to test pictures, to test these theories about how the universe works. So because of that, I wanted to spend a few minutes just talking about what telescopes do grossly, because they're such an important tool to informing our view of the universe. And already we've seen that it was only because of the very simple telescope that Galileo used that we were able to sort of understand the difference between the Ptolemaic universe and the Copernican universe. So this is actually the telescope idea that Newton came up with. So what happens is light comes in from one side of a telescope. Imagine it's pretty big, okay? And what it does is by a series of mirrors, it focuses that light down on something smaller. For example, an eyepiece that you can stick your eye in. So what it's basically trying to do is it's trying to take all the light that would be coming in over a big surface area and focus it onto something that's coming in right just in your eye. So why would you want to do that? Okay. Why do things look dimmer when they're farther away? Well, that's because the light from them is spreading out in all directions. So light from a candle is spreading out in all directions. If I put my eye close to the candle, it hasn't had time to spread out that much, so I'm getting a lot of the light. If the candle's far away, the light has been spread out all over the place, and my eye only intersects just a tiny sliver of all the light that's coming out. If I had a bigger eye, I'd collect more of the light coming out. But I don't have a bigger eye. But what telescopes do is they make a bigger eye and then focus all the light that's coming to hit that big mirror down to one small spot so it looks very bright. So that's the idea behind what a telescope is doing. And what you can get maybe from me drawing my arms like that is the bigger your telescope is, the better it is at doing its job. So telescopes do two things for you. They collect light quickly in large quantities. So they're basically big light buckets. Okay? They're like the net I was talking about before. The bigger my net, the more light, the more balls I'm going to catch. The bigger, more light I'm going to get per unit time. So the bigger the mirror, the bigger the lens of your telescope, the more powerful it is. Now there's a technical issue. How do you build really big lenses? Okay, it would be nice to have a lens that was 1,000 meters across. It's very difficult to build a lens that's that big. Okay. They also improve clarity, or make more precise the angular resolution. And that's a little bit harder to understand, but it's the same idea that if you look at Venus with your naked eye, it just looks like a dot. It's kind of smeared out. your eye can only see a certain angular resolution. So you can only discriminate angles that are bigger than about 1/10 of a degree across, or even a little less. But telescopes, depending on how big they are, can sharpen up those things, and you can begin, for example, to see phases of the moon of Venus, phases of Venus as opposed to just a bright, dull spot. Let me clarify that. So effectively, what telescopes do is they collect light. And the amount of light that they collect goes like their area. The bigger the area, the more light they're getting. And remember, area goes like pi r squared, where r is the radius. So if you have a telescope of a given radius, the area, the amount of area it has, goes like that radius squared. So the telescope with twice the radius has 4 times the area, therefore it collects 4 times as much light in a given amount of time. The radius of big telescopes is 4 meters. The radius of the human eye is 4 millimeters. So that's how much light your eye is getting. So if you want to compare the amount of light that a big telescope can collect per unit time compared to your eye, it's the ratio of the areas of the telescope to the eye. It should go like the ratio of the radii squared. So 4 meters compared to 4 millimeters squared. Okay? 4 millimeters is 4,000 millimeters. So now they have the same units. I can cancel the units. And I look at this ratio. This ratio is 1,000,000. So in every second, the biggest telescopes in the world are collecting a million times as much light as your eye can. So therefore much more powerful than your eye. You can see things that are 1,000,000 times as fainter than your eye. Now, even more so, telescopes are even more powerful than that. Because much like a camera, because you have an instrument on the other side of this telescope, you don't just have an eye. You could put a photographic plate, or you could put a CCD on the other end of the telescope and allow light to build up over time. In much the same way, if you're a photographer, if you let the lens, you keep the shutter open for a long time, you can expose and get, see images that you couldn't otherwise see in the dark. You know what I mean? You keep that shutter open for a long time, you collect light for a long time, the image can build up and build up and build up. So the deepest images that we regularly take with large telescopes, we point at one object we're interested in studying, and we keep that shutter open for an hour. Just keep it wide open for an hour. Just collect light for an hour with a telescope that's 8 meters across. And then close it, and then we see what kind of small image you eventually can build up. Now the other thing, like I said, is they improve angular resolution. So imagine you had 2 objects that were separated like this, that were far away. If you had a small telescope, you would see them all blurred together. But as your telescope gets bigger, you can separate it. Okay? This problem is much like, imagine you're driving on the road, and it's a very long road, it's nighttime. And when you see a car that's really far away, with its headlights on, the first thing you usually see is just one bright thing coming at you. But as that car approaches, the headlights separate, and now you can finally see that it's 2 headlights. You can only see them separate when their angular separation relative to you gets bigger than a certain amount. If you had a telescope or binoculars or something, you could see those headlights separate much earlier. The thing was farther away. Now, what do I want to say? So, the way you compare the angular resolving power of telescopes is you basically just compare their diameters. It's not the areas that they collect, it's just how big they are. So the angular resolving power of 2 telescopes goes like the ratios of their diameters. So this is an example of the kind of problem you'll get pretty regularly in this class. You might get on your homework or you might get on a test. Might be something like, let's say you have one telescope that has a diameter of 4 centimeters and another telescope that has a diameter of 12 centimeters. Which of those telescopes has better angular resolution? Okay, the bigger one does. Okay, that's easy. How many times better is the angular resolution? The angular resolution just goes like the ratio of the diameters. So since one has a diameter of 4, the other one has 12, you just take 4 divided by 12, that's 1/3. So one telescope has 3 times the resolving power of the other. there any questions about that? Okay. Now, what are we doing with these telescopes now? So in order to do all this stuff, basically what telescopes do is they manipulate light. They take lots of light and focus it in on places. That's what they're doing. Originally, the method that people used is they crafted lenses. They basically took glass, crafted glass to correct shapes. There's a whole theory of optics about how you do this with lenses. And then you can do this and focus light the way you want to. The biggest lens telescope in the world, telescope that uses lenses for the technology to focus light, is the Yerkes telescope. It's 1 meter in diameter. So it's a lens that's like this big, one single lens, like your eyeglass lens. It's this big. And this is the telescope. It's this big, huge thing. It was built in the 1890s, and it's still the largest telescope of its time in the world. The problem with lenses is glass is heavy, and the lens is warped. If you start making them bigger and heavier than that, they warp, and it's really hard to get very precise optics with a very big lens. So instead, what people use now are mirrors, okay? And you can kind of see what's going on now. This is a mock-up of a planned telescope, which is going to be the biggest in the world. It's going to be 30 meters in diameter, okay, which is bigger than this room, the mirror. And what it is, it's made of small mirrors that are oriented in sort of a parabolic shape all over a telescope. And that's used to craft out light. And what happens is the light comes down from here, bounces off this big thing, gets focused on another mirror that's sitting up here, and then that gets bounced back into this hole, and the hole is where they have like CCDs and stuff like that. It's very complicated optics. There are teams of hundreds and hundreds of people building it and working on it. The most powerful telescopes in the world, optical telescopes in the world right now that look at optical light, are the Keck telescopes in Hawaii. The Keck telescopes are telescopes that were basically built as a partnership between the University of California, so that's us, and Caltech. These telescopes are in Hawaii, and they're up at the top of Mauna Kea on the Big Island. They're 10 meters across, like I said before, and these have been used, for example, to discover that the universe is accelerating in its expansion, which I'll talk about later in this course, and other important things. You'll notice that when you see telescopes, especially the really big telescopes, they're often at the top of mountains. Okay? The reason why they're put at the top of mountains is that basically you want to put them in places where the atmosphere is thin. And you don't want to have very many clouds. You want to be able to see. These telescopes cost millions and millions of dollars, so you want to be able to use them all the time. You don't want to have to wait until it's cloudy or whatever. Now, one of the issues with the atmosphere in telescopes is the atmosphere really is sort of a nemesis of astronomers. There's all this air between us and the stuff we want to look at. And the light from the distant star will come through the atmosphere. As it travels through the atmosphere blurs the signal. It's like moving. The light kind of bounces off molecules in the atmosphere a little bit, and that blurs out the signal. So when you see stars twinkling, twinkle, twinkle, little star, the reason why stars twinkle is because the atmosphere is waving and moving, and that makes the stars twinkle. So astronomers do not like twinkling little stars. You want to go up high where there is very little atmosphere, so you get rid of that twinkle as much as possible. So you want to get above the atmosphere as much as possible. That's one reason why we like to put telescopes in space. If you make telescopes that orbit the Earth itself, then there's no atmosphere to worry about, and you can make really sharp pictures, really, really sharp images. How many people have heard of the Hubble Space Telescope? Much higher than Mars rovers. The Hubble telescope is arguably probably the most famous telescope that's ever been built. It's always in the newspaper. One of the reasons why it's always in the newspaper is it has the prettiest pictures. It just has awesome pictures. And the reason why it has such awesome pictures is because it doesn't have to worry about the atmosphere. It just looks straight at the stuff. It doesn't have to worry about all this atmosphere light coming through. The mirror of the Hubble Space Telescope is only 2.5 meters only. That's still very big. But it's much, much smaller than the meter of Keck telescopes. But yet it still makes much more beautiful images because the Keck telescopes, even though they're up high, they still have atmosphere that they have to deal with, whereas Hubble doesn't. And that's why you see these beautiful pictures from Hubble. So here's just an image of Pluto from the ground with a very good telescope. And you can see there's a little blob out here. When imaged with Hubble, you can see that there's Pluto, and there it's got a moon orbiting around it. And there are even more dramatic instances of this, but this is the kind of thing that Hubble can do. And this ground, it doesn't matter how, at some point, once you build your telescopes big enough on the ground, the atmosphere really messes you up. You sort of hit the limit of what the atmosphere will allow for imaging. There are technologies in the works that are trying to subtract out the problem of the atmosphere, but I'll talk about that later. The final thing I want to mention before I let you go is there's another reason why we put telescopes into space, and it's not just because of the atmosphere. The other reason, I'll talk about more next time, is that not all light is equal. So the electromagnetic spectrum is very, very broad. And while our eyes are very sensitive to seeing light in what's called the visible part of the electromagnetic spectrum, okay, this other kind of light, like infrared light, ultraviolet light, X-ray light, gamma rays, all this other stuff, that is also coming down. But the atmosphere shields us from most of these other types of electromagnetic radiation. X-ray, there's a lot of X-rays coming from space. So those X-rays don't make it to the ground. The atmosphere shields us. Same thing for gamma rays. And that's a good thing, right? We don't really want a lot of gamma rays hitting us from space. The atmosphere is good. It protects us. But if we want to study what's going on with gamma rays, we need to launch satellites up into space. And so that's another reason why we put instruments in space, because it allows us to actually see things that we could not see because the atmosphere is there. I'll talk more about that next time. So have a good weekend.